All right, recording is rolling. Welcome to Wednesday, November 8th. It is Inelastic Collisions Lab day, so I'm going to take the first few minutes of class to remind you guys from what you bring back to the fold of physics, what we're doing with these lab parts, this collision lab, and then send you guys back to the lab area for the rest of the class to do this collisions lab. You guys remember we're on a slightly shortened class period schedule today because got mental health day Wednesday, so got these 40-minute classes. I saw this up here too. All right, so yesterday I was showing you guys these collision carts. Right, you guys get to play with these today. Right? There's a whole track. Right. So each cart can have some mass. A blank cart by itself was 500 grams. I did go ahead and tape a couple of bar magnets onto one of these so that they'll stick together. Right? Hence inelastic. That's what inelastic collision is, right? They'll stick together, right? Now the bar magnets do have some mass, probably enough to make a difference. So here's some numbers you can have, right? So the cart, just an empty cart, is 500 grams, or if you go by kilograms, you call it 0.5 kilograms. Right? The two magnets, so this is two magnets because they take two magnets to something, right? Collectively is 100 grams. So each individual magnet is 50 grams, but both of them together is 100 grams. You can call it 0.1 kilograms if you're going with kilograms, right? Had you guys make this table yesterday, so you guys have this out ready to go. Remind you guys how this is working. So I have a pre-printed version that's a simplified version, so you can get the big idea. And then yesterday I had you guys create some extra columns, so got a little bit more into the details, right? So maybe I'll have both of these just to remind you, right? So each cart has a mass A, mass B, right? You can always stack more masses on them, change them, right? If you want to have that as like an independent variable, right? This is going to be an exploratory type lab. I'll let you choose what you want as independent variable. You can change masses, you can change initial speeds, right? Right, so just exploratory to see ultimately is momentum conserved, and then okay, so so each cart has a individual mass. You have to figure out what is its pre-collision velocity for each one. I am recommending that you leave one starting at rest. That's why I went ahead and zeroed out. The column says velocity of cart B pre-collision. I just 0, 0, 0, right? So you just have one cart just sitting there, la di da di da, and then another one goes bam, right? Just like slams into it, right? And then you want to see like post-collision, what is the velocity of the two stuck together? Right? And then these last couple of columns could be good for, let's say, the sum of momentum before the collision, sum of momentum after the collision, right? And that's the boiled down, like simplified version of that, right? Now, if you want to go extra details, right, that's where I got this extended version here. Okay. Well, how do you get the pre and post collision velocities? There's different ways you can do it. I'll leave it open to you and your teammates exactly how you want to do that. One way you could do it is I have a whole set of these speed gates back there. Right? I've seen students in the past like tape glue sticks to these carts so that the glue stick will go through and it'll give you a reading. Right? You could do it that way. Right? That's one option. Another option is you could use the meter stick function that's built into the track along with a stopwatch. You can calculate how far and how much time you could calculate the velocities. Right? And that's what I opened up some more columns here for. Right? So on the larger table, I got mass A, mass B. We got how far and how much time, so you can calculate how fast. Right? The other one, I'm recommending you start from rest. Right? And then post-collision. Well, okay, you have to get post-collision velocity too. In similar story, you could use a speed gate, maybe a second speed gate, because it'll happen bam, 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 so fast. Or you could say how far does it go and how much time, and you could calculate speed. Right? Now, if you do that method, what I've seen students oftentimes do, I mentioned this yesterday, but just worth mentioning again. What I've seen students oftentimes do is let the cart roll to rest and say, what was the stopping distance divided by the stopping time? Right? Now, if you do that, then necessarily this isn't exactly a zero friction system, right? It's supposed to simulate like a low friction system, right? But if you let it roll to a stop, well, okay, now there is friction and it will make a difference, right? So I threw this graph for you guys yesterday. Said if you do velocity versus time, if there truly was no friction, then it would just be constant velocity forever. It's gonna like roll all the way around the earth. Right? But if you let roll to a stop, you say, what is stopping distance divided by stopping time? What you're actually getting is here, the area of this triangle on a V versus T represents the distance it rolls, right? And if you divide that by the time, that's equivalent to if you had like an average velocity for that same time interval, right? What I'm saying is like this area of this triangle and this area of this rectangle are the same area. They represent the same distance, right? So you would have calculated this average velocity, which is not the velocity you're actually interested in. You're interested in like bam, that collision. What is the post-collision velocity, like right after the collision? You're interested in this one. And guys, what did I tell you guys the ratio was yesterday? Average velocity compared to the true post-collision velocity. What is that ratio? It's 1 over 2, right? You guys see it'd be half, right? You see from the graph, right? Kind of pops out of the page, yeah, right? So if you do that particular procedure, again, there's different ways you can do this lab, kind of up to you guys, right? But if you do stopping distance divided by stopping time, remember you have to double that average velocity to get the true post-collision velocity. I've seen students do this like many times over the years, and if they forget to double it to restore that value, then they say, like, why is my momentum like half of what it started with, right? And okay, well, that would be why. But double the speed, doubles the momentum. Oh yeah, and then ideally, these two momentum values should match all the way down, right? Momentum before collision, momentum after collision, right? Oh yeah, I meant to mention this gap right here. So as the day went on, the slightly modified versions of this table, right? So if you do stopping distance over stopping time, maybe you'll get like an average velocity, then you could double it, and that's what this column could be for, like doubling your average speed, right? If you do that, right? Or you could just use the speed gates and then just get the direct measurement. Maybe it's a little bit more straightforward, right? So what is momentum before and after? Ideally, these should be matched or pretty dang close, right? If we're solving textbook problems with collisions, then you assume as a starting point that these are the same value before and after, right? And then you can solve blah, 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 right? That's what we've been doing on that half page part, right? There's another physical quantity I want you guys to keep your eye on, which is kinetic energy, right? Well, if momentum is mass times velocity, what is kinetic energy? Is it 1/2 mv squared, right? So it's like the same ingredients, just you mix and match them a little bit different ways, right? You could quantify this in some number of joules, for example, right? What should happen to kinetic energy, like after compared to before the collision, right? So after the collision, should kinetic energy stay the same, increase, or decrease for inelastic collision? It should decrease. It should decrease. Inelastic collision will always go down, but right, today's lab day, you can empirically calculate it and see that for yourselves, right? And it should go down, right? The only way it would stay the same if it was elastic, that would be like perfectly bouncy, and the only way it could ever increase if it was some kind of explosion kind of thing, right? Right. So here, let's throw some posters up here. Here's momentum, it's mass times velocity. You guys got that, right? You guys are doing this perfectly inelastic collision lab, right? So if we were doing like a textbook problem, we would assume momentum is conserved, right? Now you guys are seeing, right, you're testing that out. Is that really true? And hopefully it's pretty close to true, right? I guess that's the two main posters you care about, right? All right. All right. I think I told you everything I need to tell you. Okay, again, this is kind of exploratory lab. If you want to change masses of the carts, you can do that. Stack lab weights on them. If you want to roll them at different speeds, you can do that. Change things up. Right? Just try different trials, and then yeah, by the end of class, just turn this lab into the grade tray. I will check that off to get points in the grade book for you. All right. So who's got any question? Any questions? All right. With that, I will throw all this stuff up on the projection, send you guys back to the lab area, rest of class, and I'll walk around and help you guys out. Any questions you have?